There is a nuclear reactor orbiting Earth right now that fits inside a shoebox. It was built by a Miami-based startup called City Labs. It launched on a mission called BOHR, and it is actively generating power in space as of 2026. No moving parts. No solar panels required. No refueling. Just a small block of radioactive material quietly releasing energy for decades. The engineers who built it say the technology was always possible. What changed is that artificial intelligence finally gave them a reason to need it badly enough to actually do it. Because AI, it turns out, is starving for power in places where power does not exist. And the next generation of satellites, the ones being built right now to run AI inference at the edge of the atmosphere, are about to hit a wall that solar panels simply cannot solve. Let's talk about what is actually at stake here, because this is not an abstract engineering story. This is about who controls intelligence in orbit, and what that means for every system you interact with on the ground. The satellite industry is undergoing a transformation that most people have not noticed yet. For decades, satellites did one thing well: they relayed signals. They were dumb pipes in the sky, passing data between points on the ground. Now, companies like SpaceX, Amazon, and a dozen well-funded startups are building satellites that do not just relay data. They process it. Onboard AI models are being embedded into satellites to analyze imagery, detect ships, track wildfires, route communications, and make real-time decisions without waiting for a signal to bounce back to Earth. The round-trip latency to a ground station can be anywhere from 20 milliseconds to several seconds. When you are tracking a fast-moving military asset or trying to catch a wildfire before it crowns, that delay is the difference between useful information and irrelevant information. But here is the immediate problem. Running AI inference on a satellite is not like running it on a server farm in Virginia where you can plug into the grid. Every watt of power a satellite consumes has to come from somewhere. Traditional solar panels work fine in low Earth orbit when the satellite is in sunlight. But satellites in low Earth orbit spend roughly 35% of every 90-minute orbit in complete darkness behind the Earth. Deep space missions have it far worse. At the distance of Jupiter, solar intensity drops to about 4% of what you get in Earth orbit. You cannot run a serious AI workload on 4% solar power. You cannot run it reliably on intermittent power that vanishes every 45 minutes. The entire premise of AI in space breaks down unless someone solves the energy problem first. That is what makes what City Labs just did so significant. To understand why this is hard, you have to go back to the earliest days of space-based nuclear power. The Soviet Union launched more than 30 nuclear-powered satellites between the 1960s and 1980s under a program called RORSAT. These were not batteries. They were actual fission reactors, small, but real, using enriched uranium to generate hundreds of watts of electricity. They worked. Several are still in orbit today in what engineers call a graveyard orbit, slowly decaying over centuries. NASA, meanwhile, leaned on a different technology called a radioisotope thermoelectric generator, or RTG. An RTG does not fission atoms. It uses the natural heat released by radioactive decay, usually from an isotope called plutonium-238, and converts that heat into electricity using a phenomenon called the Seebeck effect. When two different metals are joined and one end is hot while the other is cold, a voltage appears across the junction. No turbines, no steam, just heat flowing through a metal sandwich and producing current. Voyager 1, launched in 1977, still runs on an RTG. It has been generating power continuously for nearly 50 years and is now more than 24 billion kilometers from Earth. That is the technology heritage that City Labs is building on. But they have done something that nobody managed to do commercially before. They have made it small enough, affordable enough, and safe enough to launch on a commercial rocket without requiring a Department of Energy facility and a decade of approvals. The BOHR mission, named after the physicist Niels Bohr, is the first commercial nuclear power system ever flown in space by a private company. That alone would make it historically significant. But the engineering details are where it becomes extraordinary. City Labs calls their device a nano-tritium Betavoltaic battery, and it operates on a principle fundamentally different from classic RTGs. Instead of using heat from radioactive decay to drive a thermoelectric generator, Betavoltaic batteries capture the electrons emitted during beta decay directly. Tritium, a radioactive isotope of hydrogen, releases low-energy electrons called beta particles as it decays. City Labs places a tritium source in direct contact with a semiconductor, similar in concept to a solar cell, but instead of photons hitting the semiconductor and knocking electrons loose, beta particles do the job. The result is a continuous, uninterrupted electrical current with no moving parts, no heat management required, and a half-life of 12.3 years. That means after 12 years, the battery is still delivering half its original power. After 25 years, it is still producing meaningful current. For context, the average commercial satellite has a design life of 15 years. A Betavoltaic battery can outlive the satellite it powers. And because tritium is far less radioactive than plutonium-238, the regulatory burden is dramatically lower. City Labs has described the BOHR mission as a pathfinder, a proof of concept designed to demonstrate that this technology works in the actual radiation and thermal environment of space, not just in a laboratory. The results from orbit are what the entire industry has been waiting for. Here is the part that will genuinely recalibrate how you think about this. The power output of these first-generation devices is modest. We are talking microwatts to milliwatts in current commercial Betavoltaic cells. That sounds like almost nothing. A typical LED nightlight draws about 500 milliwatts. But consider the use case carefully. AI inference at the satellite level does not require the same power as training a large language model in a data center. What satellites need is not peak compute. It is reliable, uninterrupted baseline power for low-power AI chips that can run inference on compressed neural networks. Qualcomm's AI 100 Ultra chip, for example, draws around 75 watts at full inference load, but can be throttled down dramatically for edge applications. Companies like Sentient and Ada Compute are building neural inference chips that run full AI models on under 1 milliwatt of power. 1 milliwatt. And Betavoltaic batteries can already deliver that reliably. The BOHR mission is not trying to power the whole satellite. It is targeting the AI coprocessor. The vision is a hybrid architecture where solar panels handle propulsion and communication loads while a nuclear microbattery provides the constant, uninterrupted baseline power that keeps the AI chip alive through every shadow pass, every eclipse, every deep space transit where sunlight disappears entirely. When you frame it that way, the milliwatt output is not a limitation. It is exactly what the application demands. The implication is that every new satellite constellation currently in design could incorporate this technology within the current decade, with no new regulatory framework required. Walk through the physics one more time, because the elegance here is worth understanding. Tritium decays by converting a neutron in its nucleus into a proton, releasing an electron, the beta particle, and an antineutrino. That electron carries kinetic energy, typically around 5.7 kiloelectronvolts on average. When that energetic electron hits the semiconductor layer inside the Betavoltaic cell, it ionizes atoms in the material, creating electron-hole pairs, the same mechanism by which a solar panel converts sunlight into electricity. The difference is that sunlight is intermittent and directional. Beta particles are emitted continuously in all directions, day or night, in sunlight or shadow, at the distance of Pluto. Think of it like this. A solar panel is like a water wheel. It only turns when the river flows. A Betavoltaic battery is like a spring that never stops. What makes the City Labs design particularly clever is the use of tritium in gaseous form sealed within microstructured channels etched directly into the semiconductor. This maximizes the surface area in contact with the radioactive source without requiring any external containment vessel large enough to add significant mass. Mass is the enemy of everything in aerospace. A device that can be measured in grams, never requires refueling, and produces electricity across a 25-year lifespan without degrading until the isotope itself decays is not a compromise solution. It is structurally superior to any alternative for this specific application. The complications are real, and they deserve honest treatment. Tritium is still a radioactive material, and while its beta particles are so low energy that a sheet of paper stops them, meaning there is essentially zero external radiation risk to launch crews or the public, the regulatory and public perception landscape around anything nuclear is fraught. The word nuclear in a headline about satellites triggers reactions that the word Betavoltaic does not. There have already been incidents in the history of nuclear-powered satellites that damaged the technology's reputation. The Soviet Cosmos 954 satellite fell out of orbit in 1978 and scattered radioactive debris across northern Canada, contaminating 124,000 square kilometers. That was a fission reactor with enriched uranium. Betavoltaic tritium batteries are categorically different in risk profile. But regulators and the public do not always make that distinction cleanly. The second complication is the power density ceiling. Betavoltaic technology improves slowly, constrained by the physics of tritium's decay energy and the efficiency of energy conversion, which currently sits around 4 to 6%, compared to roughly 22% for good silicon solar cells. Scaling up output means scaling up tritium quantity, which reintroduces regulatory complexity. For high-power AI applications that need watts rather than milliwatts, Betavoltaics are not the answer today. That means the hybrid architecture is not a preference, it is a necessity. And hybrid systems add design complexity, failure modes, and cost. City Labs has solved one piece of a puzzle that still has many pieces missing. For you, the implications land in specific places depending on where you sit in the economy. If you work in aerospace, defense technology, or satellite operations, the BOHR mission just opened a regulatory and commercial door that has been closed for 60 years. City Labs has demonstrated the first commercial nuclear space power system, which means every satellite manufacturer now has a reference mission to point to when applying for launch approvals for similar devices. The first company to combine Betavoltaic baseline power with a sub-milliwatt AI inference chip in a production satellite constellation will have a decisive advantage in persistent, global, always-on intelligence collection. That is a capability worth tens of billions of dollars in defense and intelligence contracts. If you work in AI hardware, chip design, edge computing, embedded systems, the satellite use case is pulling demand toward an entirely new class of ultra-low-power neural inference processors. The companies building those chips right now, largely operating below mainstream awareness, are positioning themselves as critical suppliers to a market that did not exist 5 years ago. If you are an investor, the City Labs BOHR mission functions as a proof of concept that de-risks an entire category. Watch for the follow-on funding rounds in Betavoltaic power, in edge AI chips rated for space radiation, and in the satellite operators who move fastest to integrate them. The window between first demonstration and commercial scaling in aerospace is typically 3 to 7 years. That window is open right now. 50 years ago, Voyager 1 left Earth with an RTG that is still generating electricity today as it moves through interstellar space. The engineers who built it were solving a problem that seems simple in retrospect. You cannot rely on some